words, there's a 1/2 here, and P is the ratio. The larger the excess of one over the other, the larger is P, the larger is M, the larger is the cooperative length. This can be limited by the length of the chain, which is boring, or it could be limited by the energy of a helical reversal, which is also not so interesting. But it can be limited by the ratio of two free energies. And under those conditions, where the length of the chain is very long, it's, the higher the helical reversal energy, the larger will be L, when this term replaces that. And interestingly enough, the larger the chiral bias, the smaller will be L. So larger chiral bias is predicted to lead to a smaller excess of one helical sense over the other, and therefore a lower optical activity, completely counterintuitive. And also the other thing that came out of this was that the fraction of chiral units, for example, if you make a polymer, thanks Patrick, you can leave it open, Patrick, it's not necessary to close it. Patrick, leave it open, Patrick. It's open, leave it open, it's fine. And that's good. And the other thing is that if you make a polymer where like most of the units don't care for left or right, and then the ones that do care are battling with each other for the control in the majority rule, that it doesn't matter what fraction are battling with each other. It's just like a democratic system where you have not everyone votes. Sometimes you can have an election where only 10% of the people vote, and the politician who gets in control is the majority person of that 10%, and the others have no effect at all. This is predicting the same thing. And of course, we saw that worked yesterday. So here we were on the rising part of the curve of the majority rule. So the majority rule is not leading to the full excess because the P was not large enough to go over into the level part. That's why this is not all the way. But that's not the important point. The important point here is that here's the competing units, a slight excess of this one over that one, where every unit of the chain is chiral. It gives the identical result to where only about 1% of the units are having the same competition. Most of them don't care. So this is, it doesn't matter how many vote. It's the proportion of wanting left and right that gives the answer. So that's exactly the prediction that was made. And the other prediction that was made is something that we bothered to do. No one's ever seen this paper because for Mislow's 80th birthday, Jay Siegel called me up and begged me to put something in this obscure journal called the Journal of Physical Organic Chemistry, which I never read and I never publish anything. I'm an enemy of a proliferation of journals. I hate that. But Jay, we had to do the doc, and so I stuck this in there. No one will ever see it. It's got a nice, it has a nice way about it if you read this thing. It's an interesting stereochemistry. But the experiment is quite nice. Here's Jonathan, the fellow who took over from Schnee-Lifson when Schnee didn't want to deal with quenched random fields at his age. Anyhow, you can see here, this is a sergeant and soldier experiment. And you can see here the chiral center, if you don't mind that word, the chirotopic stereogenic center, is closer to the backbone here. This would be the polymer, it would be along here. Here it's further away, so this is going to have a stronger chiral bias, and this a weak chiral bias. This is a sergeant, that's a soldier. And so when the sergeant is stronger, you get a larger optical activity. When the sergeant is weaker, you get a smaller optical activity. That's sergeant. It's all perfectly expectable for a sergeant. But here's a majority rule experiment using the same entities. So here's the same soldier, but now there are two sergeants fighting with each other. And when the two sergeants are fighting with each other, and their bias toward what they want is more powerful, you get a smaller optical activity than when the bias that they're fighting with each other with is weaker, and you get a larger optical activity. You understand, Larry?
Can you say that again?
Yeah, the way you were looking, I could see. This is really deep organic chemistry now. You've got to give up all this parody stuff. False chiral. This is the old. This is the real stuff, right? That fancy talk, you know, forget about it.
Even that you have an equation where the ratio between them.
Yeah, the ratio matters, yeah.
Yeah, which is quite rare.
Yeah. Well, anyhow, what do you mean? Why is it rare, Gunther?
Well, I mean, everything is based on sum and differences of energy.
Yeah,
But
yeah.
let's say the ratio of energy is very common.
No, it's not a common thing, right? Yeah. Well, it comes out of that Poinch-Grandin Fielisi model, you know. Let me explain to Larry once again, and probably Axel doesn't know what I'm talking about. Look, Axel, look. This is not physics. This guy wants the helix to be a one-handedness. It's a sergeant, and it is a little bit of it, and here's mostly don't care. These are mixed together in the polymer randomly.
Mm-hmm.
These don't care. This 5% is giving you almost entirely one helical sense. 31,000 is close to one helical sense at this wavelength for the circular dipoles. So that's a sergeant controlling soldiers. And here's another sergeant controlling soldiers, but this sergeant speaks with a weaker voice because the chiral information is further away from the backbone. So speaking with a weaker voice, it gets less control. Perfectly reasonable.
And the soldiers
These are the soldiers.
So they don't
care. You tell a soldier to march left foot first, right foot. They're not chiral.
Right.
Now, so that's experiment A.
Mm-hmm.
Now here's experiment B. Experiment B is not a copolymer, not two, but a terpolymer, random.
Mm-hmm.
We know it's random. We can prove it's random. Here's the sergeant that speaks more loudly.
Mm-hmm.
The same as this guy. But now the counter sergeant is there. So they are fighting with each other
Mm-hmm.
with a somewhat strong voice. And
Mm-hmm.
that's the result they get. 3,900.
Yeah. So
Now here's the two sergeants fighting with each other with a weaker voice.
Mm-hmm.
And they get and the majority guy gets more of what he wants.
So x plus y is 10.
What's that? I'm sorry?
X plus y is 10, right?
X plus y is 10%.
Yeah.
That's
In both cases.
yeah, both cases.
And-
Everything's identical, sure,
And
except for the placement of the
so
stereos.
it's 4.95 to 5.05 something like that.
Yeah, x over y is 1.05.
Yeah.
That's right. Exactly.
So if you reduce it,
What do you mean reduce what?
yeah, I mean the amount of, let's say, the number of conflicting sergeants.
The number?
Of conflicting sergeants.
Yeah, you mean in other words
So going
change
below 10.
change r. That's
Yeah.
changing
Yeah,
r.
right,
See, let's
right.
go back to the equation. What Gunther is suggesting is change.
One before.
What Gunther is suggesting is changing r.
Yeah.
It won't make any difference because it cancels
But you
out.
can prove it, you said it. You can prove it by this.
Yeah, you can. I didn't do it, but the amount, the proportion of chiral units makes them. Now, of course, you can't go to zero.
Right.
R can't go to zero, then you don't get anything. Larry, do you?
Yes, I mean, but it's presumably a dynamic system. You're flipping right, left for the constituent helices all the time.
Yeah.
Essentially, you've got a background residual chiral field here from the excess of one influence over the other.
Yeah.
So, in the presence of that residual background chiral field, it's biasing, you're getting on average a bit more of
One,
the left
yeah.
than the right.
Yeah.
But it is a dynamic system.
It's a dynamic system. That's exactly right, your description. It's turning out this is not a fixed system.
Yeah.
This is an average, but
Yeah.
the speed with which it changes is quite fast, we believe, although we don't know the speed exactly. We do the barrier. We've measured the barrier by NMR. That's a different story that I didn't want to talk about now. By looking, what we did was we put some groupings in a side chain that were diastereotopic by virtue of the helix. For that purpose, you don't need to have the helix be favored one helical sense over the other, because the groups are diastereotopic by virtue of even if it's racemic. Now, if you lower this is the experiment we did, you lower the temperature, and you see the diastereotopic groups separate. As you raise the temperature and the helix changes from left to right, the diastereotopic groups change position. And using NM, the type of things that Jack Roberts, created years ago, you can tell by the shape of the exchange of the diastereotopic groups how quickly the whole thing is happening, and it's happening quite quickly. And that quickness, by the way, has to do with some technological interest in this. I've actually sold a couple of patents on this kind of thing about switches, which I'll tell you just a little inkling about in a moment.
Mark, what happens if you take...
Did you understand, Larry? Do you see what I'm saying?
What happens if you take deuterated?
No, it'll be too weak. You see you see that approximate algebraic solution of the quenched random field Ising model does not apply if delta G sub h becomes too small. Which makes sense, because if you look at the equation of delta G sub, you can't let delta G sub h go to 0. There's limits. When Jonathan made this approximate solution of the Ising model, he could only come up with that algebraic equation within certain limits of delta G sub h. Delta G sub r, the helical reversal energy can be anything.
So in the previous case, when you used actually deuterated and chiral centers on each one of the, what you call the soldiers.
You mean where they were, and they were battling with each other?
The question is how many such molecules you must have in order to ensure the endedness of the helix.
If the deuterated systems were R and S, what if the deuterated systems were?
Even if you take pure R, how many?
Of the deuterated?
I
don't know.
You have to be able to
I don't know. You mean, can the deuterated one be a sergeant? Essentially, is what you're asking. It's going to require much more than a regular sergeant, and you can see it in the chemistry. Look, I'd show you. Here's the equation for the sergeants and so approximate algebraic solution of the sergeant solid. The chiral autoparameter is directly related to delta G sub h. So if delta G sub h becomes very tiny, this will become tiny. And here's R. If this is very tiny and R is large, we know that in the deuterated system, when it's every one of them is deuterated, you get almost entirely one helical sense.
But the question
That's
is how
when
many,
R equals 1.
and how does it depend on the molecular weight?
Well, that's what I showed you yesterday. See, that was yesterday. Oh, sorry. I'm going to give you a failing grade.
No, what I'm asking is, what is the minimum molecular weight that you really can find? This is my question.
Well, here, this is the way it changes with molecular weight.
But below which molecular weight you don't find that effect?
When it's all deuterated?
Yeah, when it's fully deuterated,
And what molecular weight?
It must depend on molecular weight.
The only molecular weight where you don't find anything is where there is no polymer. As soon as, look here. As soon as you get even oligomers, you start to see some optical activity. It's just, I should have put Schneider's equations up here. I didn't put them up here, but I have them. I can show them too. You just have to look, let's put it this way. Each deuterated center is worth a calorie, a small calorie. Now, what do you need in order to get an excess of one over the other that's measured? 10 calories, 20 calories, 50 calories. Something. In the back of Iliel's stereochemistry book, there's a table that all students used to use. Conformational isomers, what's the energy, what's the proportion of one over the other as a function of energy. So you're dealing here approximately with a linear relationship with molecular weight, at the low molecular weight. So if you have 100 units, and each one wants left-handed by a single calorie, you have 100 calories. So 100 calories will give you a certain excess of one helical sense over the other. When you get high enough molecular weight, then you start dealing with nearly a kilocalorie, because that's the reversal energy. It gives you 1,000 units before you get a reversal.
I'm saying that because, in the case of crystallization, when you're comparing deuterated and non-deuterated materials,
Yeah.
always you get the same crystal structure.
Well, I know, but that's what we discussed yesterday, and the reason is that you have other forces that are overwhelming the deuterium. But in polymers, the mixing of polymers, if you take deuterated and non-deuterated polyethylene, they don't mix, except under special conditions.
Beyond a certain molecular weight.
Yeah, beyond a certain amount. Well, low enough molecular weight they mix because the entropy of mixing is high enough, but when you get to a high molecular weight, the entropy of mixing becomes so small that things don't mix unless there's some stickiness, some enthalpic term that makes them love each other.
I mean, one thing I'm a little bit puzzled with respect to, if you look to textbooks in biophysical chemistry, because we have some similar stories there, like Cantor and Schimmel.
Like what?
On statistical thermodynamics, but the biophysical chemistry.
Yeah.
And it's interesting, they always try to draw the picture based on the following simplification. You have the cooperativity, that means the addition of free energies.
Well, like, for example, in the formation of the alpha helix.
Right,
Is that what you're talking about?
right.
Yeah.
And you have, let's say, that means this grows linearly with the length of the hole, but then you have a nucleation.
Yes. Well, that's Zimbrag theory. That's the Zimbrag.
That's right.
Yeah.
Do we have any idea? I mean, the helicity of these polymer.
No, you see, Gunther, what you're talking. See, it doesn't apply here, because you see, in the helix coil transition, you nucleate the helix.
Yes.
See, the helix is not there as a matter of course.
Yes.
In an alpha helix, the helix has to be generated from a nucleating event. That's the Zimbrag theory.
Yeah.
And that nucleating event involves the fact that there are dipoles that add up and other hydrogen bonding forces. And once they get going, the helix forms. This is a system in where the helix exists independent of left and right.
Not at the level of monomers. You have to have a critical length.
Well,
I mean,
yes, you do, but the helix is. I don't know what you see. It's completely different because this system cannot exist in a non-helical form once you get several units.
Yeah, there isn't a disordered.
There's no disordered transition.
Disordered conformation.
Yeah, that's right. If you heat it hot enough to try to destroy the helix, you'll destroy the polymer.
In polypeptides, you have a disordered conformation.
That's right, exactly.
It's
Right.
not too different an energy from the
simply
helical
means that-
conformation.
That's exactly
so
right.
you can have facile
but it simply means that T by delta is
You
no.
have an ordered disordered transition. Here, it's not an ordered disordered
Yeah.
transition in that sense.
Yeah, it's just the
It
left-right.
simply means to me that T absolute temperature by delta S naught is small in your system.
I'm
Saying
sorry,
it's small.
say it again.
Temperature by nucleation entropy is extremely small in your case, so it's predetermined.
Okay, all right. If you want,
Okay.
you can say that.
Yeah, well, but let's say, because I don't really think that one needs to change the picture of statistical thermodynamics completely.
It's
just
just
a
becomes
small
minuscule.
nucleation.
It nucleates with
Right,
a minuscule
right.
energy.
It's almost
So
like-
minuscule that it just happens all the time.
Yeah.
But the one question I have,
Independent of temperature.
do you have an idea about the helical repeat in your system?
Oh, of course, we know exactly what it is.
Just to give me
I
an
can show
idea.
you a picture.
Just to give me
It's
an
a
idea.
310 helix with a
Okay.
pitch and a couple of angstroms. We know exactly what
Okay,
it is.
okay.
Everything. I mean, I don't bother to tell you everything.
No, but this is important to I want to see a picture.
Well, I can show you a picture later in my office, so I don't bother everybody. I have a model, and I can show you exactly what it looks like. And I can even show you. We even know the helical reversal. Schneider-Lipson did molecular mechanics on this. That was a treasure. Not he. What was that crazy guy he used to work with?
Russia?
Yeah.
Russia.
Not Russia, was the professor. There was a student here who couldn't work with
I
anyone
know,
but
I
Schneider.
know.
What's his name?
I know.
You know what I mean?
Yeah, I know.
Talked really
Yeah, I
fast,
know,
and
I know, I know.
he was a little bit,
Yeah,
but brilliant
I
in
know.
computers.
Nobody.
Yeah. Schneider, we had the best in the world do force field calculation. And so we know what it looks like physically, the helix. Besides the stretched fiber, diagram, the X-ray diffraction, also gave information too, so we know everything.
In these curves, can you normalize it so one has a relative?
Here?
Yeah.
Yeah, well, you could. This up here is 100% of one helical sense. More.
I mean, what does that approximately mean? I mean, one could enably think maybe
wait a
3,000
second.
divided
No,
by
I'm
6,000
sorry.
and a half or
This,
something.
wait. This does not, because if we went to still lower temperatures, this would go up even higher.
Yes.
So
I mean-
I don't know exactly where this is right now. I'm sorry.
But depends a bit what these units mean. I mean, if you
Well, this is
Maybe
just
it's-
a mole ellipticity. That's it.
uh-huh.
It's just mole ellipticity. There's a correlation with. I can't. I'm very sorry, but I can't remember right now what the percentage of leftover right is in this case.
And you don't know the sign could be either of the two.
Well, you see, we did a force field calculation.
Mm.
And the force field calculation we put in, not in the deuterium case, but in the case where we had citronellic acid. The force field tells us the helical sense. Now, at one time, I tried to get a lot of people to look by AFM to see the actual sense of the helix directly, but it was never successful. But I think it would be successful now, because the technology has greatly increased in the last few years. You can actually get down now with single molecule and see that.
You said that you have only left and right, and you don't have order disorder.
No disorder.
Transition, like what you were saying. But if you look on these kinks there,
Look on what?
these kinks there that
The
you're
kink.
forming,
Yeah.
then this may be regarded as a kind of
This may be
disorder.
what?
May be regarded as a disorder.
Well, it's only a kink. It's only a kink. This reversal does not propagate through the whole chain and destroy the helical conformation.
So the mechanism is that once you form such a kink, you cannot. I mean,
What-
what is the transition from left to right? It has completely resolved, or it goes through such kind of kinks?
No, it goes through these kinks. It doesn't go through a whole disorder. Lifson looked at it, by force field calculations. And we know, I can show you a macromolecules paper that we published together, where we know how many units are necessary to form the kink. Only a few units. And the kink is traveling up and down. It's completely different from a protein. In a protein, when you start to get a disorder, it'll propagate through the whole chain. Even in a protein, by the way, modern work shows that so-called coiled protein structures are still helical. But the helix is often broken.
That's one of my specialities. It's the polyproline 2 helix.
That's right. This is what Neville is
Right.
interested in.
It so happens that
Yeah.
this technique of Raman optical activity is wonderfully sensitive to polyproline 2 helix.
Uh-huh.
And we've shown that it's a dominant structural element in natively unfolded proteins.
Exactly. This is what I talk to Neville about
And
that all
so
the time.
it's an extended left-handed helix, and
Yeah.
there's no internal hydrogen bonds. It's stabilized by hydrogen bonding to water. So it's flexible. It's
Right.
what I call a careful disorderliness.
That's right.
Because it's all set up. It can snap over to an alpha helix very easily.
Right.
In fact, it snaps over to a hydrated alpha helix, and we see this in our experiments. And this is what I'll be talking about in the symposium that you'll miss. And in fact, it's because.
But I mean, I know about this work because Neville and I are very good friends, and we
Yeah,
talk about it all the
yeah.
time. People had thought for years that the disordered form of the alpha helix was some kind of terrible mess, but it's not a mess at all. It's just a very flexible helix of a different
This
parameters.
is now a very important theme in protein science, because more and more proteins are being found that are disordered in their native functional state, especially brain proteins and that sort of thing. And there's often very extended disordered sequences in native folded proteins, and they're all set up ready to undergo, like the disorder to, when they bind, they snap over like to an alpha helix.
Yeah.
And
Or perhaps go the other way to an Alzheimer's
yes,
disease.
that's right. And in fact, there was a meeting in the first international meeting on unfolded proteins as a big new theme in protein science in Budapest last year. I was invited, and I was surprised to find, I knew our work was making some sort of impact. I was surprised to find that the people in the field now, they see that the two techniques that have what's helped to establish this field is NMR
And Raman optical
optical activity,
Yeah,
which
that's
is
great.
very gratifying.
Now, I wish you'd send me, when you get back to England,
Yes.
would you try and remember to
Yeah,
send me
sure.
some of those papers?
Yeah. But this idea, a careful disorderliness, I got that from Moby Dick. This is one of my favourite quotations. It says, you know, they're chasing whales all over the world. They set off on a 2-3 year trip, and he says somewhere there are some enterprises in which a careful disorderliness is the true method. So, you know, if you're going off in one direction but you see whale spouts in the other direction, you must have the flexibility, off you go there. And I think this is what, you know, protein function is all about, this careful disorderliness, and that's what the polyproline 2 helix is all about. It's a flexible...
Well, that's life,
thing.
isn't it?
Yeah.
That's what life is like.
Yeah,
To be
yeah.
successful in life, you've got to be prepared.
And that's what research is all about, isn't it? You know, a careful disorderliness. You must be flexible. You know, it doesn't fit to what the administrators of science and research, you know, grant committees want. You know, they want fixed goal, but that's not how it works. You want a careful disorderliness.
I like the metaphor or the simile, whatever you might call it. Sure, it's
In fact, I put it in the front. That's the quotation in the front of the second edition of my book. In fact.
yeah, careful disorder is the, you know the hint. We had a hint years ago because of liquid crystals. You know, if you take a protein, a peptide, and you put it in dichloroacetic acid, you lose the alpha helical CD.
Yes.
You know, it's no longer an alpha helix. So everybody said, well, it's a random coil. That was the word that was used, disorderly. But in fact, if you raise the concentration, at a concentration not that much higher than the concentration necessary to form a liquid crystal from a bona fide alpha helix, you get a liquid crystal, which shows that, as Larry says, it has the potential to get straightened out, to choose a different way. And the crowding of the liquid crystal forces that. So that's absolutely, yeah. I'm lucky that I'm friends with a guy at NYU that Larry's friends with who clues me in on all this stuff. Colin Bach with the proline 2. He wrote a paper on this that was widely quoted. One of the most widely quoted papers in biochemistry.
We did a collaboration with him. One of his peptides that he claimed from NMR and CD was
proline 2.
And people like Chiraga have been very hostile. But we showed from ROA that it's PP2. In fact, we've recently done, you know, an ab initio simulation of the PP2, of the ROA spectrum you expect from a PP2, and it fits beautifully to our observed spectrum.
Chiraga's often hostile.
Yeah.
I once talked in front of Chiraga about Lifson's work, and he had the nerve to jump all over it, you know, but it was, you know, that's Chiraga. Privately, I'll tell you some things about him, but about his hostilities.
You know, he used to be always a member of our scientific, you know, we have a scientific committee to judge the department. He always used to come to the memory to stay there and have a discussion with him.
Give a hard time. Yeah, but he had to be quiet in the face of Schnee. Schnee would calm him, you know, because looking from up here. Anyhow, so is this satisfactory now? Do you see what's... No one will ever read this paper, but it's a nice thing because it shows that less gives more. In a cooperative situation, the less force applied between the cooperating entities, the higher the level of cooperation, and the larger, therefore, the effect.
It's not much more than this.
Well, we're on the rising slope here.
Okay.
I didn't see any reason. I could have repeated this experiment in ways. It was hard enough to. This experiment was very difficult to do, and I could have continued it. But what's the point? You know, I could keep going and make it higher.
And that's exactly what your formula shows then.
Yeah,
Right.
This is exactly what the formula shows. Namely that delta G sub H becomes smaller, the chiral bias becomes smaller than the optical activity.
Couldn't this be an example, though, that you don't want to do too many experiments because the first one fits
No, they would all fit. I could easily manipulate this into much larger numbers. I know how to do it, but I don't want to waste my time. I already understand it. That's why I've only published 100-something papers in my life. Again. Before we explain everything about the origin of homochirality, which is next, I want to show you a little trick we did with this. Here's the equation again, just spelled out a little bit. The chiral order parameter is A alpha over alpha max, so this was the M. Here's the error function, and this is all the stuff that was in it. When P is 1/2, this gets simplified to the equation that I showed you before. That's all. Why did we take this out? Because we wanted to consider the possibility that the competing units were not enantiomers of each other. In other words, the unit that wants the left-handed helix and the unit that wants the right-handed helix are structurally different. They're enantiomeric, but they're not enantiomers of each other. They're structurally different. And that, I thought, would lead to an interesting, a crazy situation here if they're structurally different from each other. See, here they're structurally identical. This is this case we had before. The competing units in the majority rule experiment are enantiomers of each other. So P star equals 1/2. Because P star equals delta G of one unit divided by delta G of the combination of the other two. This is the chiral bias of A divided by the chiral bias of A plus the chiral bias of B. That's how P star is defined. And if delta GA equals delta GB, then this is 1/2. And if this becomes 1/2, then the equation simplifies to the one that we had before, and everything that we said before is true. But the more interesting one right now is if A and B have different structures. If A and B have different structures, then delta GA does not equal delta GB anymore. And P star, therefore, can be anything. It doesn't have to be 1/2. And not only that, P star will be temperature dependent. Of course, delta GA and delta GB are temperature dependent, but their temperature dependencies are identical because they're enantiomers. Therefore, P star equals 1/2 independent of temperature when you have enantiomers competing with each other. But when they're structurally different, then P star is temperature dependent and can be anything. What does that mean? It means that I can control the proportion of the competing units that want left and right by synthesis. Hey, 90-10, 50-40, I can do anything I want. What I can do is make this by synthesis something and then change the temperature. And when the temperature reaches the point where P star happens to equal the proportion that I put in here synthetically, the optical activity will go to 0. Because P will equal P star and it'll cancel out. You'll get a 0. Larry, do you understand? Yeah? You understand? It's a very crazy system, see. So what that means, therefore, is that I can make a series of polymers where I vary P, and in every one of those polymers there'll be some temperature at which the optical activity will go to 0. Above that temperature, the optical activity will rise, and below that it'll fall, or vice versa, one way or the other, depending on left versus right and plus and minus. And so you can get a series of lines, In fact, it would be an interesting way to measure temperature. Completely no electricity, just light. An optical thing. So we did that experiment. There it is. Every one of these lines corresponds to a different value of P. In other words, a different value of how much I put in of the structurally different I want left and I want right. And that's each line corresponds to that. And the reason the lines are straighter here and more sloped over here is that the cooperativity is higher at lower temperatures, because at lower temperatures you get fewer helical reversals. The thermal input into the helical reversal. In other words, you get a larger value of L, so you get a straighter line. And this is very nice. And then we made liquid crystals out of each of these. And here's a typical example of one of them. And this shows the same liquid crystal property in a lyotropic liquid crystal, not a thermotropic, but a lyotropic, because these form solution phase liquid crystals, the kind that were described by Lars Onsager first to explain the birefringence of tobacco mosaic virus, which no one understood. That was the original source of the understanding of liquid crystals came from Onsager, that it was an entropic phenomenon. These form Onsager type liquid crystals in solution. And this is the kind of effect that you get. See, as you're approaching zero, you're losing the twisted pneumatic phase. This is phenomenologically identical to the thermotropic things that you see on your watch or in your car. You know, they're called twisted pneumatics. It doesn't matter to go into the detail right now. The fact is that this is a micron path length. A micron path length. And the optical activity, this is the real optical activity. That's a liquid crystal, twisted pneumatic liquid crystals. In other words, as we approach this point, before we reach zero and go down here, we're observing 60 degrees. The polar image is going like this. And you're at a micron path length. Just incredible to see. So, and I had a film, I don't show the film here today, where we can measure temperature this way, and we wrote a patent on this, you see. It's probably useless, but so what? Somebody bought it.
Put it between 2 parameters.
Yeah, so we actually did it. I showed that in China.
Fever and the disparity of temperature.
But people do that already. People have patches that do that. There are liquid crystal patches, which probably are better than this. But it's phenomenologically fascinating. So this is a sort of distortion of the majority rule experiment where the competing units are structurally different, and therefore you get a temperature dependence, and this is what you can make out of that.
In some of these fridges, you have these temperature things that tell you. Is that the sort of thing?
It would be. It's a little different because in those things, it's color that changes, and the color is changing because of the pitch of a cholesteric liquid crystal. In this case, it's more related to the kind of liquid crystal display that you have in your car on the dashboard or in a watch or something like that. You see, that's why the effect is so much bigger. They're huge effects. So anyhow, so now let's get to. I've taken too long already. You know, when this guy, this is it essentially. One more after this. This guy from Australia we were talking about, found a circularly polarized light in outer space, and so Jonathan and I wrote a letter to Science, which they published, pointing out that you get a small excess of one enantiomer over another from the circularly polarized light in outer space, and if those enantiomers find their way into a polymer, then the polymer could take on a large excess of one helical sense, even if the wrong enantiomer is there. And this is a mechanism of movement toward homochirality. It's not a movement toward, it's a movement even toward homochirality with bias, because the circular polarized light would give you the bias. So you get the bias from the circularly polarized light, and the majority rule, if it forms a polymer that takes a kind of a helical conformation, that you start to move toward that thing. But of course, this is useless unless something else happens. And the other thing that happens is something that I've never demonstrated experimentally, although I tried, but I didn't try hard enough. I'll show you why. Watch. Let's say that you have a helical conformation. Just allow a helical conformation. What the hell? Allow a helical conformation. Now, along this helical conformation, you have R groups, you have S groups, and the R groups and the S groups are in. There's a slight excess of one over the other. Although that's not necessary, as I'll show you. They could be 50-50 too. It doesn't make any difference. Now, here's another chain, right? With R groups and S groups, yeah? I don't care what the proportion is. It could be 50-50. Forget about the bias. That's an unhappy situation. That's enthalpically higher in energy than it has to be. Why? Because the helix, something that forms a helix doesn't like to get out of the helical conformation. So the helix has to have, if these are random with each other, R units and S units that are in the wrong helical sense. It's just going to statistically be true. How can the system solve that problem? The system can solve that problem by allowing an interconversion between these. And what will be the consequence, the enthalpic consequence of such an epimerization, which is the word that we use in stereochemistry? What would be the consequence of the epimerization? The consequence of the epimerization is that statistically, one, you would get some chains which would be all R, and some chains which would be all S. So you start with a mess, see, you start with a mess, and you end up with a true racemic mixture in a polymer. This is the setup for the homochirality of life. That's what you need. You can't get it. If you don't have that epimerization of these units, and you form a polymer, you can't go anywhere because the thing is strangled by the conflict. But as soon as you allow an epimerization, which is absolutely perfectly reasonable and known in several amino acids, even under conditions of a reasonable life, aspartic acid, for example, let alone, over the eons of time, or with the sugars or whatever, then this will be enthalpic. Now, if you start out with 50-50 R and S, this will happen. It makes no difference. But you'll go to a true racemic mixture. If you start with an excess of one over the other, then an interesting thing would happen. At first, let's say there's more R than S. If there's more R than S, there'll be a desire for the system to go that way. Which means that as you go more R over S, the helix will begin to increase toward the direction that the R wants. The optical activity, therefore, will increase. Enthalpy will show, as you look at it, you'll see you'll see the optical activity growing in front of your eyes as soon as you start the epimerization, which we can do synthetically with light or some other way, or with a binaphthyl. I have all kinds of ways. You can turn it on and off. As soon as you turn this on, you should see the optical activity increase if you had an excess of one over the other. But that enthalpic force that's increasing the excess of one helical sense over the other will then be overcome by the fact that you are lowering the entropy, because you're taking a mixture and making it into a pure substance. And as the entropy takes over, the epimerization will eventually lead you to the same place as if you had 50-50. So the prediction, therefore, is this. You start out like that, with a little excess, you go up, and then you go to the racemic state. Now, I called Jonathan up about this. I said, Jonathan, sounds like statistical physics. So he wrote, God knows, Monte Carlo, I don't know what the hell he's doing over there, but something with this kind of stuff. Monte Carlo something. He wrote a Ising model and then with Monte Carlo steps and, with this idea. And you can see it. We have many, I have many graphs like this where he changed the time and the length and, all kinds of stuff. And you see all kinds of things. But you can see here what's going on, you see? Can you see? You can't see the colors here.
No, we can.
Okay, we can.
You don't look alike here.
Das ist vielleicht irgendwie not enough.
No, can you see the color?
We can see it.
Oh, you have to see the color. It doesn't matter. Yeah, if you like. This is green. The excess of left or right is averaged over all the chains. You see the optical activity goes up, and then the entropy starts to take over, because you want to get the minimum free energy, and so you go down to 0. And there's the excess of RS side groups averaged all the chains, which happens in this particular example to track this, but it's not necessary. So it's exactly what the qualitative prediction is. And these are properties of individual chains. You see, even though you're going to the racemic state, even though you're going to a zero optical activity, you're producing chains which are fully left-handed and fully right-handed, with an order parameter of 1. You're producing chains which are overwhelmingly R and overwhelmingly S. That's why this is so high. So what you're doing is taking a mess and producing a racemic mixture. Now, this comes to a place then, what I wrote, who's the great, what's the matter with me? Who did Gattarelli work for in England? The great stereochemist who wrote about the chiral biases.
Mason.
What?
Stephen Mason.
Stephen who?
Mason.
Mason, yes, thank you, Mason, yeah. I wrote to Mason.
He died about
I know he died. I wrote to Mason and he wrote back to me. I asked Mislow about this. Those are the two. I have a memory that Albert Einstein was asked about the origin of homochirality. And that this is a memory I have, and that Einstein said, I don't know if I dreamt it, or where I heard this, Mislow said he never heard it before. Mason said he never heard it before. I don't know who else to ask, because those guys...
What did he say?
What did Einstein say?
Yeah.
2 equal runners, 1 tripped. That's what Einstein... I don't know that he said it. They deny... I didn't say it. Believe me, I'm not that clever. But it's a very interesting idea. Whoever said it, I think Einstein said it. Look, here you can't have 2 equal runners. You see, to have homochirality, forget about the bias. The bias is trivial. It doesn't make any difference. The bias is not even worth discussing. There's a million ways to get the bias. Gunther is showing us ways yesterday. Forget about the bias. The bias is uninteresting. What's interesting is to have systems that can compete with each other, and you can't have that if you have mirror images mixed in single molecules, and life is polymeric. This is a mechanism for polymers to become homochiral. Once the polymers become homochiral, the bias becomes a simple thing. One will take over the other for a million reasons. I can name a million of them here right now. So this is my contribution here. That's what you paid my half there. Show that.
Why do you have this maximum after a short time?
I'm sorry?
Why do you have this maximum after a short time?
It's a trivial. It's a detail of
statistical.
Yeah, it's a detail.
Yeah.
I have other graphs here. I can show you all kinds of things. Go up like that. Go up like that. Like this. You know, it depends on the detail. We tried to do this. You know how I tried to do it? I tried to do it with a friend of mine in Japan, a student of Yoshio Okamoto's Yashima. He was a kid when I first knew him. Now he's got some kind of institute or something. And I said to him, he was interested in polyacetylenes. I said, let's put on the polyacetylene a binaphthyl, see, and even one that I can turn on and off with light that goes like this. And he tried a little bit. And I don't have the patience. I'm not anymore 40 years old. You know, if I were 40, I would demonstrate this, but it's okay. I spoke to Jonathan the other day. We should publish this someplace. Publish this idea.
That's not published.
No. No one knows about this. This is completely secret. This is the first place I don't know I ever revealed it when anyone would know
a special
about it.
Issue.
What?
You're going to have after this conference a special issue.
In what journal? Another physical organic chemistry journal?
Origin of Life.
No one reads this kind of thing.
Everybody's reading this.
No,
There's a lot of.
I was thinking this belongs in chirality.
So this becomes special to the conference, and therefore we have to have.
Oh, come on! No, this is already. This idea. I'm not going to put it in the origin. I'll put it there, but I'll put it someplace else also.
It's okay. It's okay. But you're going to put it there as well.
I'll put it in the other place first, so they don't say I published it. Where should I publish it? No one reads chirality either, right? Who reads chirality?
I mean, if you can get it over in a couple of pages, a Jack's communication is
You think they'd take that? Not if I get that idiot from Yale,
Oh,
that moron from Yale.
who's that?
She's a moron.
I mean, there's a
What's
lot
her
of
name? That woman from Yale is just a big trouble.
you know, there's a lot of interest amongst chemists in this, and it's really good polymer chemistry, and I think Jack's would be good if it was just 2 pages.
Yeah, I could make it short.
High impact.
I could make it short.
You know,
With the theory, with the Monte Carlo calculation to show what would happen. Could do. Anyhow, so look, so.
but don't put it in, say, a dedicated polymer science journal.
No. I would never put this in macromolecules. No, forget about it.
This is the origin
This
of
is
Nobody
the
reads
origin of
those.
origin, right?
It's a stereotype.
It's
It's an interesting thing. Anyhow, so you like it? Te
I think there
gusta?
are some analogous system in crystallization.
Maybe. Anyhow,
What about science on nature? I know that's a real pain.
I'm,
to deal with those.
my life is almost over. Now look, here's, that's what I belong to, the Herman Mark Polymer Research Institute. That's the man who made the clothes hangers out of platinum. Herman Mark. This is who supported me. National Science, the Navy supported me for a long time. They thought I would do something useful, but then they realized the truth. Petroleum Research Fund always gave me money, but now I understand they're trying to also be useful, so I don't forget about it. I still have money from these guys. I have a postdoc coming who's working on peptide nucleic acids that I didn't tell you about. 2 PhD theses finished already, one in Italy and one in Brooklyn, and I haven't published a single word. I wish someone here could explain to me what's going on. I have the chapter, I can show you the data. And the theoretical analysis was Schnee Lifson, God bless his memory. I know a troublesome character, but to me, he was like a father and a treasure. The Weizmann Institute. And Jonathan Sellinger is a lovely young man, now a chair of science in Ohio at Kent State University and editor of PhysRev something or other. And he did the quenched field. And the experimental collaborations on the deuterated system with all of the with all of the precise molecular weights, and stuff like that. I spent 6 months in Japan, and that was Takahiro Sato, who's a professor now in Osaka. Akio Teramoto, who had a tragic situation happen to him. He was retired. He went to Kyoto to work for a while, and then he came back to his house. And one day, and he is the most lovely man. If you look him up, Akio Teramoto published the most beautiful things, an exquisite scientist. One day, he had a park near his house with a little, like a cliff, and he put a ladder to climb down to pluck a beautiful flower, and it collapsed, and he fell, and he's paralyzed now. Unbelievable. I mean, this is a man that anyone would love. He's the sweetest, most gentle man. And in fact, Schneier and I went to his laboratory and had a little conference together about the deuterated system. And I think we all have this philosophy. Because of what Einstein said, that Neville Cullenbach has in his office now, which is that if we knew what we were doing, it wouldn't be research. That's it.
Thank you. Thanks, Mark. These were very impressive lectures.
Thank you.
And we need to think.
Well, we need to.
Raphael, what do you think?
Mayor wants to say something. I think everybody has some more to say about their own work. I mean, not about this, about their own.
Think about it. Yeah, no, just about that. At least roughly what I described, I think, a few times ago. But the problem with the model, when you have this kind of epimerization, you go to a mixture of R and S polymers.
Separate polymers.
Yes, but if you couple this kind of mechanism with a continuous activated polymerization and to form these polymers, to allow this epimerization between the chains so that it favors the homochiral peptides.
Yeah.
And then you continuously destroy them. You have some cycles, and these cycles you have truly autocatalytic effects, network autocatalysis. And in this kind of system, you really observe the bifurcation.
I see.
Yeah.
I think what
But
you
you
need
won't
is,
get a bias without some.
Yes, without any
Without
bias.
bias.
Yes, you really can build.
No, but the bias I don't care about. The bias is.
Yeah, I totally agree.
I
Yes.
always thought the bias was trivial, but listening to Gunther yesterday,
Yeah.
you know, I've been even more convinced me how trivial the bias
Yes,
is.
yes. But you can build the kind of system that Gunther described yesterday on this kind of epimerization patterns, and it's really the motor, the bifurcation pattern.
For the autocatalytic effect, that requires some sort of feedback. You know, you
Yeah.
have to have the polymer that's formed has to influence the new one.
That's why you need continuous recycling so that
That
you destroy
requires-
the polymers and you
That
improve.
requires some kind of a template effect.
so is it, for example, feasible to think of melting polymer? Would that be one way of destroying it and reassembling it?
It's like crystallization.
How easy is it to epimerize peptides? How easy?
Well, aspartic acid is quite easy. In fact, people measure the age. You can measure the age of some animals that lived only 1,000 years ago by looking at how much racemic aspartic acid is.
Yeah, but this is in solid phase, but in liquid, in water, it's few hundreds of years, it's totally epimerized.
In fact, I think in the age when you get older, that one finds D amino acids in your eye. In your eye. No, in your eye. In your eye.
What do you think?
But that's just
Yeah, but let's say
aspartic.
this is amino acid, but you have to have, let's say, a mechanism by which the epimerization, okay, of course you could also do it at the amino acid, but let's say in the direct bonding would take place in the oligomers. Right?
Good, yeah. I mean, you have to
It's
have
faster,
some...
epimerization is faster in peptides than in free amino acid, actually.
Yeah, because you have because you don't have the negative charge on the oxygen.
They should really look together, because this APET and your model have indeed some.
Yeah, I think it's the main core idea.
So that's my swan song.
No? After the
No, I think it's perhaps a good idea. We can have a